All right, in the last part of 10.4, we're going to look at how to do derivatives in polar form. So we have this equation in polar form, r is a function of theta. Well, how are we going to deal with the derivative of y with respect to x? Basically, how are we going to deal with the slope of the tangent line in rectangular format? So what are we going to do? Basically, we got to think of x as r cosine theta. Now, r is going to be this weird function of theta, right? So it's going to be a function of theta. So x is r cosine theta, and y is r times sine theta. Again, r is this weird function of theta. So what we do is sort of akin to what we did with parametric form. The derivative of y with respect to x, we take the derivative of y with respect to theta and then divide that by the derivative of x with respect to theta. Okay? Now, if you think about derivative of y with respect to theta, it's the derivative of this f theta sine theta with respect to theta. If you do that, because we're doing a multiplication here, f theta times sine theta, we have to use a product rule. So it's going to be f theta, the derivative of sine is cosine, so f theta times cosine, plus the derivative of f theta times normal sine theta. So basically, this is just a product rule of the derivative of y with respect to theta. A lot of times I'll think of this f theta as r and this f prime theta as r prime because of r is equal to the function of theta. So if you see me writing r and r prime, that's what I'm writing for r here and r prime there. Now the same thing goes with x. So with x, we have a product rule. So we take normal f of theta times the derivative of cosine. Derivative of cosine is negative sine. So you end up with negative f theta sine plus derivative of the function in front, f prime theta, times normal cosine. So basically, this is just product rule of this derivative divided by product rule of this. Derivative requires us to do a product rule. So here's what I'd like you to do. This formula is going to be provided on a formula sheet, but go ahead and find the derivative of this polar equation, r equals 5. And obviously that derivative will allow us to find the slope of the tangent line when theta equals pi over 4 and when theta equals 0. Go ahead and do that. All right, so we start with our derivative in polar form, f theta cosine theta plus f prime theta sine theta, divided by a negative f theta sine theta plus f prime theta cosine theta. Now, I'm going to write r as for f theta and f prime I'm just going to write as r prime. So you'll notice that with this circle, r equals 5 is a circle, obviously, of radius 5. The derivative is 0. So the derivative of y with respect to x, I can take this equation. Everywhere I see an f theta, I can replace it with a 5. And every time I see an f prime theta, I can replace it with the 0. So I have 5 cosine theta plus 0 times sine theta, divided by negative 5 sine theta plus 0 times cosine theta. And that's what we get. Obviously, if we want to cancel and simplify, 0 times sine theta is 0. 0 times cosine theta is also 0. So we end up with 5 cosine theta over negative 5 sine theta. That's just negative cosine over sine. So that's the derivative of y with respect to x, all in terms of theta. Now, at various values of theta, we can obviously find the slope. So if we, for instance, plug in pi over 4 for theta, plug in pi over 4 into cosine, you end up with root 2 over 2. Do the same for sine, you also end up with root 2 over 2. So you end up with -1 as your answer. So the derivative of y with respect to x is -1. That means, in terms of rectangular ideas, the slope at that point where theta equals pi over 4 of the tangent line is -1. So you can see that here. I've tried to create that point right here. This is the circle of radius 5. We have a point here. You can imagine that this tangent line has slope -1. All right. Tangent line I'm kind of trying to trace with my cursor there. So there you go. That's the idea. Now, obviously, if we plug in a different value of theta, for instance, if we plug in theta equals 0, well, if I plug in 0 into cosine, I get a 1. If I plug in 0 into sine, I get a 0. So this is undefined. And what that means is that the slope of the tangent line is, well, in this case, it's infinite. Sometimes it's actually undefined because we don't have a tangent line. Other times, like this one, the slope is infinite. So if you were to graph this, we're talking at the point 5, 0. The slope, the tangent line is a vertical line. So there we go. So that's the idea of derivatives. Now, r equals 5 was a really nice simple polar equation. Obviously, our polar equations can get more complex. So I would like you to try example 6 on your own. Find the derivative and then find the slope when theta equals 0. So first off, find the derivative function for r equals 5 cosine 2 theta. And then when theta equals 0, figure out what that means. Go ahead and push pause and try that on your own. All right, so 5 cosine 2 theta. When you take the derivative of that with respect to theta, derivative of cosine is negative sine, and then since we have to multiply times 2, that's the derivative of the inside function, we end up with -10 sine 2 theta as my derivative of r, or you can think of it as f prime. So all I'm going to do is I'm going to take this equation, and every time I see an f theta, I have to replace it with 5 times cosine 2 theta. And every time I see an f prime theta, I have to replace it with -10 sine 2 theta. Now that gives me a fairly complicated first derivative. I end up with, on the top, 5 cosine 2 theta times cosine of theta minus 10 sine 2 theta times sine theta, right? Again, I'm replacing this f prime theta with this -10 sine 2 theta. On the bottom, I'm getting -5 cosine 2 theta times sine theta minus 10 sine 2 theta times cosine theta. Again, that's a mouthful, but that's what it is, okay? There's no really great way to simplify this. You could go through a long process of doing trig identities with different angles to simplify this if you want to. It's not worth our time to do right now. So there you go. Complicated derivative, but that's what it is. Now, when you plug in 0 into this derivative, cosine of 0, anytime you do cosine of 2 times 0, you just get cosine of 0. So we get 5 cosine 0 minus 10 sine 0 sine 0. Minus 5 cosine 0 sine 0 minus 10 sine 0 cosine 0. Remember, every time you plug in sine 0, you get a 0. So this part of the numerator goes away. Every time you plug in 0 into cosine, you get a 1. So you just get 5 times 1 times 1. So you get 5 in the numerator. In the denominator here, we got sine 0 gives me 0. That'll 0 that thing out. Another sine 0 will 0 this thing out. So you just end up with 0 in the denominator again. And once again, you end up with a vertical tangent line. This is undefined, obviously, so we're getting a vertical tangent line there at theta equals 0. So these things can get real complicated real quickly. I want you to do one more. Try to do this. So go ahead and push pause on the video and do this one. So r equals 3 plus 3 cosine theta. The derivative of that, well, derivative of 3 is 0. Derivative of 3 cosine theta is negative 3 sine theta. So every time you see an f theta, replace it with 3 plus 3 cosine theta. Every time you see an f prime, replace that with negative 3 sine theta in our formula. So you end up with 3 plus 3 cosine theta, quantity times cosine theta, minus 3 sine theta times another sine theta, and then negative 3 plus 3 cosine theta, quantity times sine theta, minus 3 sine theta cosine theta. That's a really long first derivative, but that's what happens. Now again, if you wanted to simplify this, you could take some time and simplify and rewrite and distribute this cosine, distribute that cosine, do some cosine squared, sine squared, identities maybe, all that kind of good stuff. But in the end, this is what it is. Again, a real kind of messy looking thing. If you plug in 0, remember every time you plug in 0 to cosine, you get a 1. Every time you plug in 0 to sine, you get a 0. So you get 3 plus 3, that should be a 6, I believe. 6 times 1 minus 0. Oops, that should be a 6 on top there. So if you plug in 0, you get 6 on top. If you plug in 0 here, you get, again, negative 6 times 0, that's 0. Minus 3 times 0 times 1, that's 0. So you get 0 in the denominator. Again, this is undefined. That means, in this case, that is a vertical tangent. So notice what that was. 3 plus 3 cosine theta. That was that cardioid that we dealt with when we sketched graphs. That was a cardioid. So that's the idea. So we can find derivatives of y with respect to x, even if we have a polar form of an equation. All right, that's a very nice thing to have.